Hi, my name is Frank Flederer. I'm a research assistant at the Chair of Aerospace Information Technology at the University of Würzburg. Today I'm going to show you a software framework that we have been developed in the last few years, which does not just follow the model-based approach, it enhances the model-based approach by extending the formal model with information from the source code. We call our framework Corfu. Corfu stands for Configurable Onboard Software Framework for you, and it follows the already mentioned extended model-based approach. We will see in a later slide how this exactly works. Corfu builds on top of the real-time operating system Rhodos. Rhodos does not only provide a real-time scheduling and a hardware abstraction layer, it also comes with a communication middleware, which is following a publish-subscribe principle. And this is also what Corfu uses. So let's start with an overview over the development process. Okay, this is very much, so let's break it down to separate steps. We start with the formal model. So the basic architecture of software that uses Corfu is an app-centric design. That means we have separate apps that implement different features. And all those apps interact with each other. In the total software, we have three main entities. The first are the already mentioned apps. Then we have nodes. Nodes represent computing nodes on a satellite or software images. So on a satellite, we usually have different computing nodes. We might have 2 or 3 redundant onboard computers. We might have payload computers for scientific operations. And those nodes might share a few apps, but not every app is part of every node. And then the third are the topics. So the topics are communication channels that connect the different apps. So one app might publish data and the other apps might subscribe them in order to process them. So these are the main entities that we have in our formal model. Let's have a look more detailed into these entities. The first element that we can describe in app models are threads. So threads are independent execution paths that are executed quasi-parallel. So the scheduling is accomplished by the operating system, but on this side we can define some parameters that influence the scheduling. So we can define the priority, we can define some timing properties. So this piece of information is already described in the Apple model and is formally available for verification. The second main property is the internal communication interface. The internal communication means here the communication on board. So not the communication between space and ground, but the communication on board. That means the communication between the apps and the communication between the nodes. And as I have already mentioned, we use the publish-subscribe middleware implementation of the Rhodos operating system, and therefore our communication on the internal part is the communication with topics. So we define topic subscriptions and topic publications. That means which types of data are published and which types of data are subscribed. The other part is the external communication interface. So this means the communication between the space and the ground. So each app contributes to the total communication interface of the satellite. This includes telecommands on which apps react on, telemetry, So we have two types of telemetry. The one is the real-time telemetry, the other one is the extended telemetry. And last, we can define different parameters, either compile time parameters or runtime parameters. So compile time parameters just means they are then hardly coded either by generated code or templated code. Runtime parameters can be changed also at the run of the satellite. So this is the main overview of the app. Let's head to the node model. A node is quite easy to model. So first it has a list of apps that should be instantiated on the node. And we have a list of topics that is required in order to connect all those apps. And finally, we connect the subscription and publication of apps to topic instances on the node. Good. The next part of the development process is the generation of code. That means we take the formal model and source code templates and generate source code depending on those information. So our generator parses the full model configuration. It uses a library which parses the data and provides a C++ data structure accordingly. It processes the template files. So we have template files that contain placeholders, variables, control structures in order to build a full C++ file. So the final source code is divided into 3 hierarchy levels. The first hierarchy is a generic app class. So this is not generated code at all. It's just some superclass that is already provided by Corfu. And the generated code just inherits from this generic class. This generated class is an abstract class that contains methods for handling telecommands, handling topic subscription, executing thread code, and so on. And all those abstract methods have to be implemented by the user eventually. So the user creates an own class that inherits from the generated code. And the user app class just contains code that implements the desired behavior. So it is not necessary for the user to implement telecommand handling and so on. This is already encapsulated into the generated and generic app class, and the user can fully concentrate on implementing the behavior of the apps. For the node, this is similar. We also have a generic class that is directly provided by Corfu. We have a generated node class that instantiates the user app classes, creates the topics, and gluing everything together. And for the nodes, the user does not have to create any code at all. Everything is already available in the model and is directly generated. And then we have the final compilation part. It is quite simple. We have the developer source code, we have the generated source code, and we have some Corfu libraries that implement generic behavior, for example, those generic app and node classes. And everything is just compiled and linked together into a software binary. So that means for each node that we have defined in the model, a software binary is created. So this is the classical model-based approach. We had our formal model, generating code, and compiling everything together. What we have here new is that we have a feedback from the developer source code to the model. So we have a code analyzer that extracts some information into an extracted model, which can then be used by the generator or at runtime. So our code analyzer uses the Clang abstract syntax tree. Most of you might know Clang as a compiler frontend for LLVM, but you can also use it standalone and their functionality of parsing. This is what we do here. We don't want to implement our own parser because C++ is very complex. Based on the abstract syntax tree, we extract information from the source code. We will see an example in the next few slides. And those information is used to extend the formal model. So we have our formal model on the one side, we have our extracted model on the other side, which contains the extracted information from the source code. And in total, we call it the extended model. And this information can be used at compile time in order, for example, to provide additional features or improving performance, or also in runtime, or a combination of both. So we show you an example of using this extended model by implementing a simple logging system. You might have, or you might know, logging systems that provide a way to print strings and maybe some parameters in order to be print out, or in our case, sent to ground. Usually this is used at development phase. But the problem here is that on a satellite system, we usually have very constrained resources. And that means if we want to put a lot of strings into an executable and on the downlink, that might not work very well. And what I'm going to show you now is that we use the extended model in order to provide a more resource-constrained implementation of such a logging system. So basically we have a macro that is called log. It contains the severity information and some string. In this example, I just left the parameters, but we already have it implemented that also supports parameters. So this macro is defined as follows. It just calls a log function, passing the severity, and calling a hash function. So it just creates a hash value out from the string here. And the clue here is that the hash function is defined to being a const expression. That means the hash value is already calculated at the compile time, and consequently the string does not land in the binary file if we don't use it in another place. In this case, we just save the hash value, which is much shorter than usually a string. And the same goes for transmitting the logging information to the ground. In order to remap from the hash value back to the string, we extract those information into the extended model. So we look in the code for the log messages, save the hash value, the log messages, and the parameter types into the extracted model. And this model is then used by the ground software in order to have the mapping available. This is only a very simple example. There are many more ways to extend the model and to profit from this extended model. So that's it with our development process, with the feedback from the source code back to the model. Let's have a quick look over several other features of our framework. First, unit testing. In unit testing, we want to test the user's source code. So the source code that has been developed manually by the user of the framework. Just recall that we have these three types of classes. We have our generic app class, which is provided by Corfu, the generated app class, so the generated code by Corfu, and then the user app class. And this below here is what we want to test. This user code uses features of the generated and the generic classes. So we have an interface from those generic and generated code down to the user code. And these two classes already implement behavior of the onboard software, which is not required by the unit testing. And on the other side, unit testing can be made easier if we would provide additional features to those classes. And therefore, in order to provide the unit testing, we have our own generic app testing class. We have our own generated app testing class, so based on the model of the app. And what we do here is that when we compile the testing code, the user app class will inherit from the testing classes instead of the normal app classes. In the real onboard software, it still uses these generated and generic app classes. So that means we don't change this app class. So this generated app testing classes and the generated app classes are using the same name, which means we can reuse our user code without modifying it. But those unit testing classes provide ways to receive information about the direction of the user code. So if the user code emits telemetry data, if it emits topic data, and so on. And these all information can then be used by the test code in order to test the behavior of the user code. Corfu is quite new in its development, even if we started the development a few years ago. There is a satellite mission that is currently being developed that carries Corfu. The mission is called InnoCube. It is a CubeSat developed by the University of Würzburg and the Technical University of Berlin. Its purpose is to have a technical demonstration of two techniques. The one is skip the harness, which replaces a wired bus between the different computing nodes with a radio bus. The other technology that is shown by this satellite mission is called Wally, which is a battery directly integrated into the structure. Corfu comes with the concept of apps being distributed over several nodes, or several nodes might execute the same apps. And this software design architecture is very good for the InnoCube mission because we have 6 different computing nodes. That means 6 different configuration of nodes and combinations of apps. And we have more than 20 different apps on the satellite. We come to the conclusion. So, Corfu is a software seed that can be used for creating custom software satellites, which includes onboard software and also ground software. It's still early in development, and the approach of creating an extended model enables new features and improved performance.